Welcome back. We're going to continue our discussion on valence electrons and valence orbital. I do want to say that the information that will be contained on this particular screen and the following screen is not entirely new. Okay, I have thrown in the idea of when we talked about cations and anions electronic configuration, where do we remove the electrons from and where do we add electrons from. Okay, and pretty much the outermost orbital is the furthest to the right is the valence orbital. Sometimes you could have more than one, but still the outermost one is the valence, but then I'll explain with few examples what I mean by that. Okay, but general, the orbital furthest to the right is the outermost valence, but sometimes you might have two, that is the outermost, and then the one before that could also be a valence orbital. Okay, and whenever you add or remove electrons, you always do it to the furthest right orbital, and then if you have to take more, then you go one. I think I have shown examples for that, so I'm just going to reconvene that because this is a topic in itself that deserves a due respect. So that's why I'm recovering some of that material here, and this would actually lead into something else that's a tad bit new, right? So valence orbitals, the outermost, you see I'm putting S in the bracket. That means you could have just one orbital which is valence, or you could have more than one that as a collective could be valence orbitals. Okay, the outermost, which is the one furthest to the right. And obviously, electrons contained in the valence orbitals are called valence electrons. All right, I don't think I probably will quiz you on those because that's just fact. Okay, and I have repeatedly told you, and I will keep repeating this because this is an idea that it takes a while for the mind or the brain to register it. Okay, cation is positively charged, and in chemistry, positive charge means something being lost or removed. Okay, so electrons are lost from the valence orbital, and if your element has +1 charge, means 1 electron lost, +2 means 2 electrons lost. Okay, so Mg2 plus means 2 electrons are lost, but from where? We've already went through this, but before I put it up, let me actually write it down. First, you got to figure out where this Mg is in the sequence. Mg is in band 3s. And then we know the atomic number of magnesium is 12. Okay, first you got to write it for Mg12, and then we can worry about Mg2 plus. Okay, because I think many of you may not have developed the expertise yet to go directly. So I do recommend you go step by step. I'm not going to, stop and do all this. I'm just going to pretend I have the correct configuration here. This is for magnesium. Magnesium 2 plus means you have lost 2 electrons, and I worked this out before when I did, so it's 10. So where do we lose the 2 electrons from? It's from the outermost one. So that would be 1s2, 2s2, 2p6. And let's go see if, so I wrote the configuration. And then I circle and identify which one is my valence orbital, which is the outermost one, that is the furthest to the right from the left, because we always write from left to right. Okay, and then I had removed the 2. So let's look at anion. Okay, electrons are added to the valence orbital. -1 means you add 1 electron, -2 means we add 2 electrons, and 3 minus. Again, I'm going to work it out here first. Nitrogen, the atomic number is 7. You may want to start practicing this way, like I have told you before, because I think it takes time to really get super comfortable with all this. So N3 minus means we're adding 3. Where do we add it? Well, we just have to add it to the outermost orbital, which is furthest to the right. And P can hold 6, remember? So we can add the 3 more. So that's 2p6. So let me go back and put this up. Now, at this point, I do want to say something, okay? Because this is very important. We're not going to spend a considerable amount of time on this particular video talking about bonding, but I do want to put the seed so that it's in your brain somewhere registered. Bonding means for any two elements to bond, only the valence electrons can be involved in bonding. For instance, say a nitrogen were to bond with another nitrogen, like a nitrogen gas, okay? Nitrogen has to bond with another nitrogen, right? You cannot use all 7, okay? You can only use the outermost electrons or the valence electron, which would be the 2p3, okay? That is, you can only have 3 electrons available for bonding, which is why each nitrogen gives its 3 electrons. Again, this is not something you have to remember excessively at this point. I'm just saying that so that you kind of understand. If you've never seen, you will learn more about this. Nitrogen has triple bond. Why? Because each nitrogen can only provide 3 electrons on its end. So when 2 nitrogens bond, you end up having, because a bond is made up of 2 electrons, period. Okay? A bond requires 2 electrons. So bonding only happens between the valence electrons of each element that are involved in bonding. This is something I want you to remember, but not necessarily go into depth at this point. So there are alternate ways to determine valence orbitals and valence electrons. One of them is to write your condensed electronic configuration, okay? Once you write the condensed electronic configuration, whatever orbitals left in the condensed is basically your valence orbital, and the electrons contained in them are valence electrons. So we've already learned it. Let's go. Let me do one, and then I'll have you practice the remaining, okay? Because I think if I do too many, you would get accustomed to me doing more, and which leaves you less to practice, okay? So titanium. All right, titanium is in row 4, so we have to use domain 2 to write, or domain 2 rules to write our electronic configuration, right? So first let's write the regular one, and then we can switch. Okay, I'm comfortable, so I'm doing it directly. I don't recommend you do it. You do it the way I have taught you. So for S2 and 3D, I believe you'll be left with 2, okay? But this is not correct. We got to switch. So the D has to, 3s have to go with the 3s, the 4s have to go with the 4s. So the correct electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, and 4s2. Right? Very good. This is the correct electronic configuration. Now, to write the condensed electronic configuration, we have to locate the noble gas in the row prior to the row containing titanium, and that would be argon. So argon appears to be in the 3p band, so we strike out everything up until 3p, replace that with AR in square brackets, and write whatever's left. So this is what I mean by, yes, we have 2 valence orbital, but what the one outermost is what's going to get affected first when we add or remove. But then this also has an equal opportunity of getting lost. So the question asks you, write the condensed electronic configuration. I have done it. And determine the outermost valence orbitals. Outermost, I guess in this case I should have asked you, but I have put plural, so what I'm really referring to is write me everything, identify everything there is, and in this case we have 2, so it's 3D and 4S. And that's what I was referring to in the question. Now, do you see how everything is so related? There's nothing we have learned so far as being put to waste. Everything has been used up until this point. Every time we learn something, we're using every other information we have learned to make sense of what we are doing. All right, so I'll leave you there with that, and I'll have you practice the remaining 3 that's on the screen, and then you can raise. If you have questions, please do ask. And I will see you with one tad bit information in the next video, and we're going to wrap this concept of valence because we have a few more things that we have to learn. All right, so stay tuned.